So let's look at the formal definition of p-value. Let me back up. Let's look at the theorem for the p-value. And then you can think this one as the form another definition. So we have a excuse me. We have a test statistic such that the large value of W gives evidence that the H1 is true. And for sample point X, we define the Px is equal to supremum under the null hypothesis that Wx is greater or equal to W little x. So this W capital X is the random variable, and W little x is the realized value of test statistic. And then this Px is the valid p-value, which means that so p-value is the biggest possible probability under the null hypothesis of the Wx is greater or equal to the realized value of the test statistic. So it is the biggest possible probability under H0 that the sample the real value test statistic as extreme as the test statistic as extreme as the realized test statistic as the realized test statistic. So we are looking at the extreme of our probability that our test statistic is greater or equal to calculated the test statistics. So as I said, again, this is a random variable. So then this is the realized value. So if our random variable has the probability that the random variable is test statistic is greater or equal to realized test statistic. If that probability is very small, then we are highly likely to reject the null hypothesis, and if it is large, we are not going to reject the null hypothesis. And so the proof is omitted. Then we are going to look at alternative way to define a valid p-value. So let W be the test statistic such that the large values of W give evidence that the H1 is true. And then we define the sufficient statistic. We define sufficient statistic for data where the data is the value under the null hypothesis. If we define the Px is equal to probability that the Wx is greater or equal to W little x, given S equal to Sx, then it is also valid p-value. So you can define the p-value by using the sufficient statistic. So let me give an example. So we have a normal random sample from theta and mean theta and the variance sigma square. Sigma square is unknown. And we consider testing theta is equal to theta 0 versus theta is not equal to theta 0. So it is the two-sided test. And we use the likelihood ratio test statistic. Absolute value of x bar minus theta 0 divided by sample standard deviation divided by square root of n. So let's compute the p-value of the likelihood ratio test statistic Wx. So by definition, it's going to be the supremum under the null hypothesis P, the probability that the Wx is greater or equal to W little x. it is going to be expressed like this. So if you take out absolute value, then we have x bar minus theta 0 divided by s divided by square root of n will equal wx, or x bar minus w0, x bar minus theta 0 divided by s divided by square root of n less than or equal to minus wx. Then under the null hypothesis, this fraction follows the t distribution with n-1 degrees of freedom. It is and that is 2 times the power that Tn minus 1 is greater or equal to W little x. And the p value is p value is the 2 times the probability that the t distribution with n-1 division of freedom is greater or equal to x bar minus theta 0 divided by s divided by square root of n. That's our p value. And then if you look at this p value, so we have our p-value here. And then if you look at this p-value, we reject H0 if and only if the p-value is less than or equal to alpha. That is the reject if and only if then this is you get this. So if you solve this entire expression in terms of the samples, your x bar minus theta 0 divided by s divided square root n is greater or equal to the quantile based on t distribution with n minus 1 degrees of freedom with alpha divided by 2, which this means that if you have t distribution n minus 1, the probability of this shaded area is the alpha over 2. And then here is this the probability that t random variable based on n minus 1 degrees of freedom is greater than t n minus 1 alpha 2 critical value is equal to alpha divided by 2. So So our test is reject H0 if and only if from this p-value the standardization is greater or equal to quantile value of the based on the t distribution n minus 1 degrees of freedom and alpha divided by 2 quantiles. And then this is the same as the likelihood ratio test. So you can see that the equivalence of the test based on p-value and the likelihood ratio test. So let's calculate p-value based on numerical values. So we have sample size equal to 16 and x bar is equal to 1.5. The calculated x bar is equal to 1.5 and sample standard deviation equal to 1. And then the null, under the null hypothesis, the theta 0 is equal to 1. So let's calculate the p-value. So if we calculate the p-value, just plug in the numbers, then we can get the probability that so p-value is 2 times probability that t n minus 1 is greater or equal to 2, which is the 0.064. And then so we do not reject H0 at level 0.5, but we do reject H0 under level 0.1. So again, we have the normal random sample, and let's assume that we know the sigma square, and we would like to consider testing null hypothesis theta is less than or equal to theta 0 versus the alternative is theta is equal to theta 0. Let's calculate the p-value and what is the LRT size alpha test based on p-value. So So consider the W prime is the function of LRT statistic, and this bigger value gives the evidence that H1 is true. And then So we can have this expression, the supremum of p theta is the theta is less than or equal to theta 0 is the x bar minus theta 0 divided by sigma divided square root n squared or equal to the realized sample mean minus theta 0 divided by sigma divided by square root n. Then we can change this theta 0 to theta because it is depending on the depends on theta. This probability depends on the theta. So this is we have the Z is the standard normal because we already shown that the supremum is achieved in the theta 0. So this kind of real in the last is kind of probability that Z is greater or equal to x bar minus theta 0 divided by sigma divided by square root n. So if we reject H-Lipfan only if the p-value is less than or equal to alpha, so if we use this expression, then we reject the probability that Z is greater or equal to x little x bar minus theta 0 divided by sigma divided by square root n is less than or equal to alpha. So we get the p-value and then we construct a test if this p-value is less than or equal to alpha. This means that if you solve this in the probability part, this x bar minus theta 0 divided by sigma divided by square root n is greater or equal to z alpha. This is x bar is greater or equal to theta 0 plus sigma divided by square root n times z alpha. So we get the same test as like ratio test size alpha test as derived before. So the test based on p-value is same as like a ratio test size alpha test we have derived before. So there is no discrepancy between test based on p-value and test based on likelihood ratio test statistic. So we can use these two interchangeably. I mean, you can, and people use this p-value with the test statistic calculated from the test procedure. So let me stop on here and I will see you in the next class.